Newton's law of cooling. When a hot object is left in surrounding air that is at a lower temperature, the object's temperature will decrease exponentially, leveling off towards the surrounding air temperature. This leveling off will correspond to a horizontal asymptote in the graph of the temperature function. Unless the room temperature is 0, this will correspond to a vertical shift of the generic exponential decay function. Newton's law of cooling. The temperature of an object, T, in surrounding air with temperature T sub S will behave according to the formula T of T equals AE raised to the KT power plus T sub S, where T is time, A is a constant determined by the initial temperature of the object, K is a constant, the continuous rate of cooling of the object. While an equation of the form T of T equals AB raised to the T power plus T sub S could be used, the continuous growth form is more common. Example 7. A cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed into a 35-degree refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees. If you must wait until the cheesecake has cooled to 70 degrees before you eat it, how long will you have to wait? Since the surrounding air temperature in the refrigerator is 35 degrees, the cheesecake's temperature will decay exponentially towards 35, following the equation T of T equals AE raised to the KT power plus 35. We know the initial temperature was 765, so T of 0 equals 165. Substituting in these values, 165 equals AE raised to the K multiplied by 0 power plus 35. 165 equals A plus 35. A equals 130. We were given another pair of data, T of 10 equals 150, which we can use to solve for K. 150 equals 130e raised to the K 10 power plus 35. 115 equals 130e raised to the K 10 power. 115 divided by 130 equals e raised to the 10k power. Natural log of 115 divided by 130 equals 10k. K equals natural log of 115 divided by 130, all divided by 10, equals negative 0.0123. Together, this gives us the equation for cooling. T of T equals 130e raised to the negative 0.0123 t power plus 35. Now we can solve for the time it will take for the temperature to cool to 70 degrees. 70 equals 130e raised to the negative 0.0123 t power plus 35. 35 equals 130e raised to the negative 0.0123 t power. 35 divided by 130 equals e raised to the negative 0.0123 t power. Natural log of 35 divided by 130 equals negative 0.0123 t. T equals the natural log of 35 divided by 130. All divided by negative 0.0123 is approximately 106.68. It will take about 107 minutes or 1 hour and 47 minutes for the cheesecake to cool. Of course, if you like your cheesecake served chilled, you'd have to wait a bit longer. Try it now. A pitcher of water at 40 degrees Fahrenheit is placed into a 70-degree room. 1 hour later, the temperature has risen to 45 degrees. How long will it take for the temperature to rise to 60 degrees? Logarithmic scales. For quantities that vary greatly in magnitude, a standard scale of measurement is not always effective, and utilizing logarithms can make the values more manageable. For example, if the average distances from the sun to the major bodies in our solar system are listed, you see they vary greatly. Placed on a linear scale, one with equally spaced values, these values get bunched up. However, computing the logarithm of each value and plotting these new values on a number line results in a more manageable graph and makes the relative distances more apparent. Sometimes, as shown above, the scale on a logarithmic number line will show the log values, but more commonly, the original values are listed as powers of 10, as shown below. Example 8. Estimate the value point P on the log scale above. The point P appears to be halfway between -2 and -1 in log value. So if V is the value of the point, log of V is approximately -1.5. Rewriting in exponential form, V is approximately 10 raised to the -1.5 power equals 0.0316. Example 9. Place the number 6,000 on a logarithmic scale. Since log of 6,000 is approximately 3.8, this point would belong on the log scale about. Try it now. Plot the data in the table below on a logarithmic scale. Notice that on the log scale above, example 8, the visual distance on the scale between points A and B and between C and D is the same. When looking at the values these points correspond to, notice B is 10 times the value of A and D is 10 times the value of C. A visual linear difference between points corresponds to a relative ratio change between the corresponding values. Logarithms are used for showing these relative changes. For example, comparing $1 million to $10,000, the first is 100 times larger than the second. 1 million divided by 10,000 equals 100 equals 10 squared. Likewise, comparing $1,000 to $10, the first is 100 times larger than the second. 1,000 divided by 10 equals 100 equals 10 squared. When one quantity is roughly 10 times larger than another, we say it is 1 order of magnitude larger. In both cases described above, the first number was 2 orders of magnitude larger than the second. Notice that the order of magnitude can be found as the common logarithm of the ratio of the quantities. On the log scale above, B is 1 order of magnitude larger than A, and D is 1 order of magnitude larger than C. Orders of magnitude. Given two values A and B to determine how many orders of magnitude A is greater than B. Difference in orders of magnitude equals log of A divided by B. Example 10. On the log scale above, example 8, how many orders of magnitude larger is C than B? The value B corresponds to 10 squared equals 100. The value C corresponds to 10 to the 5th power equals 100,000. The relative change is 100,000 divided by 100 equals 1,000 equals 10 to the 5th power divided by 10 to the 2nd power equals 10 cubed. The log of this value is 3. C is 3 orders of magnitude greater than B, which can be seen on the log scale by the visual difference between the points on the scale. Try it now. Using the table from Try It Now number 5, what is the difference of order of magnitude between the softest sound a human can hear and the launching of the space shuttle? Earthquakes. An example of a logarithmic scale is the moment magnitude scale, MMS, used for earthquakes. The scale is commonly and mistakenly called the Richter scale, which was a very similar scale succeeded by the MMS. The moment magnitude scale. For an earthquake with seismic moment S, a measurement of Earth movement, the MMS value or magnitude of the earthquake is M equals 2/3 logs of S divided by S sub 0, where sub 0 equals 10 raised to the 16th power is a baseline measure for the seismic moment. Example 11. If one earthquake has an MMS magnitude of 6.0 and another has a magnitude of 8.0, how much more powerful in terms of Earth movement is the second earthquake?